Hydrogen is seen by many as the ultimate clean fuel, able to heat homes and power vehicles without any carbon emissions. But to actually produce it traditionally requires a lot of energy in itself, often outweighing the end benefits. But a new and innovative project based at the Maltings Organic Waste Treatment Site in Yorkshire is now successfully using waste matter to produce hydrogen, whilst capturing carbon in the process. Funded by the Net Zero Innovation Portfolio from the Department for Energy Security and Net Zero, H2 Boost brings a number of partners together in this ambitious project.
We are taking in the feedstock that the Maltings are providing, which is our own blend of food waste and paper waste and other mixtures. We're using dark fermentation to produce the hydrogen, and then the CO2, which is separated from the hydrogen, will be used to capture the carbon in algae or cyanobacteria. Previously, we'd been undertaking experiments within the labs. We now have a full working demonstration scale. We're able to demonstrate how we can scale this up and how it can actually be used in industry and taken further forward.
I don't think there are many people doing biohydrogen at this scale. So there's probably stuff going on in labs, obviously, but pre-commercial scale, there's not a lot going on. So there's been real challenges in trying to make hydrogen go where we want it to go and not leak out of various things. You know, it's an extremely small molecule, but also be able to use the hydrogen in an effective way. We've got an extremely large bit of software that's running the whole site, which is being tweaked and altered all the time to try and optimize it now. And so the challenge has been really, I suppose, compact site, getting the design right for the activities that are taking place, but also then integrating that with complicated software and reporting and recording so that everybody gets all the bits they want. So I think we're there.
This is our feedstock tank. So this is a 5,000 litre tank where food waste goes in, and then this flows through a system. So this is the first step of our dark fermentation. We basically take digestate, which is full of interesting microbes. We heat treat it to produce microbes that will give us hydrogen, but also to take out anything that will produce methane. This inoculum then flows through into our dark fermenters. So these are two 5,000 litre systems. They are heated and hydrogen is constantly coming off these along with CO2. This gas then goes into our hydrogen upgrading. So we can take the hydrogen from anywhere between 35 to 70% and increase that which is needed for hydrogen in the transport sector. The CO2 from this process then goes all the way back down into the algae and cyanocapture.
The algae and cyanocapture stage involves two separate systems, each of which capture the carbon from the process in different biological ways. Both of these teams have worked extensively to identify the strains of algae and cyanobacteria and the operating conditions that provide the best results.
Our setup involves two different stages. The first one is CO2 absorption and solubilization in digestate. We are using digestate as culture media for microalgae cultivation. As soon as we solubilize as much CO2 as possible in the digestate, we transfer that into the photobioreactors in which we cultivate microalgae. We have two different photobioreactors, one without the addition of CO2, the other one with CO2 already dissolved in it, that we are comparing as a baseline. At the end of the process, we will harvest the biomass. This biomass will be then processed for carbon sequestration in the long term. So what we do with the final effluent is to close the loop by recirculating it into the dilution of the digestate we are using for cultivating the microalgae.
Cyanocapture is an Oxford-based startup, and we build scalable carbon capture technology using cyanobacteria. Cyanobacteria is one of the fastest growing photosynthetic organism on Earth that is known to mankind so far. And we use these strains as one of our carbon capturing mechanisms, basically meaning we are exploiting the photosynthetic ability of these strains and then employing for the purpose of carbon capture as well as potential reuse of nutrients from any downstream process. As a part of H2 Boost project, we are trying to reuse the downstream waste from the process, which is CO2 as well as digestate, which can be raw materials for the growth of cyanobacteria. So we dry the liquid culture and that becomes a dried biomass, and the biomass is something that can be pyrolyzed and becomes biochar, and it is a durable form of carbon, which means we can permanently lock that carbon and then make sure this entire process is a net zero process, which is very essential for the production of hydrogen. So after that, this is also a form that where we can biomanufacture different byproducts. So that includes insulin, collagen, and then many pigments that cyanobacteria is known to produce.
The results so far are providing a lot of encouragement to the various partners involved, and providing hope that producing hydrogen in this way can make a significant contribution in decarbonising economies around the world.
Biohydrogen, I think, is truly important, not only for the UK, so we do an awful lot of work in the rest of the world. We have a big base in India, and electrification of the transport system is just not going to work overseas, and the biohydrogen way forward is potential opportunity for those countries to actually go down the full renewable route and the low carbon route. But I think we've had a good time with the rest of the partners. We've learned a huge amount, which has been great. That's always good from a collaborative project. There's been some real challenges along the way, but we've been able to adapt. Knowledge has been shared, and I think the common goal about getting biohydrogen and biogas out of the same feedstock, we're coming to that fruition point now.
The design of this kit is a new design. It's never been done before because obviously the dark fermentation is new added to the AD, so we have a complete new design which was done quite quickly. The ultimate goal is to be able to commercialise this and to get this out there, whether it's on a small scale or even a large scale. If we can produce enough hydrogen that's of the quality and standard that we are hoping to get, then the aim is to develop this even further to the next stage, and we can prove to industry and other companies out there that have waste that they don't currently use that we do have a very valuable and exciting way of disposing of their waste to create a new fuel in hydrogen.